Hey guys, Mr. Catlin here with practice problems 1.10 for your homework. And we're jumping in with this map of a park problem. And one map of a park has a scale, and I'm going to do this with a small table. It has a scale, so drawing to actual. Always good to do this table when you have a scale, where 1 inch is 1,000 feet. And the other one, I'll do in blue over here, has a scale where 1 inch is 500 feet, the actual size. And the question is, which map that you draw would be larger? And naturally, you want to lean toward the 1,000 feet because it's a bigger number. It's like, oh, it's a bigger number. It's going to be a bigger map. But you got to remember that this is the scale. This is how we're shrinking it down. So every 1,000 feet on the map is only going to be an inch in the drawing, where 500 feet over here is going to be an inch on the drawing. So one way that you can easily prove this is to pick a common. And since they're dividing by 1,000 here, and they're dividing by 500 over here to get from right to left, let's pick a common length of 2,000. Let's do 2,000. Okay, so 2,000 feet on both of these. Now, like I said, the common analogy here is that we're dividing to get over to how big that would be in the drawing. So on the left side, you know, your scale factor is times 1,000. So you would divide by 1,000 to bounce back. And 2,000 divided by 1,000 would be a 2-inch section on that map. Now over here, your scale factor is different because they're multiplying by 500 to get over. Therefore, they're dividing by 500 to get on the other side. So when you take 2,000 and you divide by 500, 500, 1,000, 1,500, 2,000, that is 4 inches long. And last I checked, 4 inches is longer on a map than 2 inches is on a map. So this would actually be, this one over here would be the larger map than the first, because the drawing would be twice as big, because you're only cutting it, you know, every 500 feet into an inch instead of every 1,000 into an inch. And we learned that when we did our triangle activity on Wednesday. We saw that the smaller triangles were built when you had a scale number that was larger on the actual size, because you're dividing by a larger number, you get a smaller quotient. All right, let's look at number 2. So if quadrilateral Q is a scaled copy of P, so we've got quadrilateral Q over here somewhere, and it's been drawn with a scale factor of 3, so it's bigger, right? And this is not drawn to scale. This is just me saying, hey, here's Q. Okay, so there's quadrilateral Q. And well, let me move my face over here. What is the perimeter of Q? Ooh, okay, so perimeter, we're going to know what that means, which might take us a minute to remember. But I think we do know what scale factor means. Every one of these is going to get multiplied by 3, right? So 7 times 3, 15 times 3, 25 times 3. 7 times 3 is 21. 15 times 3 is 45. 25 times 3 is 75. Okay, so we got our new lengths in our 3 times bigger shape, and perimeter means all sides added together. Okay, it's the distance around the figure. Or the perimeter, we're going to walk the perimeter of the shape. We're going to go all the way around it. So we're going to do 21 plus 90. I'm going to go ahead and add my 45s together and make 90, and then 75. Okay, this came from my 240s that I had. Okay, so 240s make 90. This is just easy math for me to do. And then 6, 1 and 5 make 6. And then 16 plus 2 is 18. And there's my answer, 186 units. Pretty easy problem. Okay, scale everything times 3 and then add everything together. And that's how I do that type of problem. I'll throw myself back over here. Let's go to the next page. Let's see if I got any more in 1.9. I think there are some more on the 3rd page. Let's take a look at it. Why don't we? And I won't save my results. All right, number 3, last one for this video. All right. Triangle DEF, which is over y'all, is a scaled copy of triangle ABC, over y'all. And for each of the following parts of triangle ABC, identify the corresponding part of the triangle DEF. So this goes back to previous lessons where we're doing corresponding parts. Okay, so angles, segments, we got to be able to identify these things. So let's start with pinpointing where we're at first. So ABC angle. ABC would be the angle that connects those points and is created right there. Okay, so angle ABC, which I've highlighted in red, corresponds to the same location right here. And we're going to identify that as angle D, corresponding to A, E, corresponding to B, F, corresponding to C. So we would write that like this. We're going to say it corresponds. We're just going to draw an arrow to angle. I'm going to use the angle symbol, D, E, F, right? And then BCA, let's do that one in green. So BCA is this top angle that I'm going to draw in green up here. I'm going to do 2 angle marks to notate that. That corresponds, obviously, up here on top where the F is. But we're going to call that BCA, same location, EFD. So that corresponds with angle E, F, and D. All right, let's do another color. Let's go blue. Excuse me. For segment AC. So AC would be from A to C, this line segment in blue that I'm highlighting. And that corresponds to DF. So we want to write, I'm going to use segment notation, which we haven't really talked about much, but line segment, and then your letters underneath. That is representative of line segment DF. Last one, let's go orange. Segment BA is down here on the bottom, B to A, or A to B, however you want to think about it. And that corresponds with this section over here that's in orange. B to A goes with E to D. So E, D. And there you go. There's your finished homework for practice problems 1.9.